Force-time graph analysis. Force-time graph analysis. We have a variable force, and that's over here, right? It's constant for a while, and then it changes. It's applied on a 2.5 kilogram cart at rest, which starts moving in the positive x direction along a track. The force-time graph shows the applied force at different times. And okay, force on the y-axis, you always lead with that one, and time on the x-axis. From 0 to 4 seconds, right, that's from here to here, what is the impulse delivered by the applied force to the cart? What is the change in momentum of the cart? And then what is the velocity of the cart at t equals 4 seconds? Then from 4 to 6 seconds, what is the impulse delivered? And what is the change in momentum of the cart? And then from t equals 0 to 6 seconds, that's the whole thing here, what is the impulse delivered by the applied force to the cart? What's the change in momentum of the cart? And then what is the velocity of the cart at 6 seconds? Here's the key point we need to know. Impulse is what? It's F delta t. Okay, force times the time that it's exerted over. On a force time graph, impulse will be the area between the force line and the x-axis. So if we want to go from 0 to 4, that area there is the impulse. Impulse is also defined as the change in momentum, where the change in momentum is mvf minus mv0. So let's do the first part to find the impulse. We want to go from 0 to 4 seconds. So we mark off our 4 seconds here, and we bound it by the force. And we've already said the area under that, or within that section, is going to be the impulse. So what do we have? We have a rectangle. The base is 4 seconds. See how we write the units there? And the height is 6 newtons. This is kind of fun, right? It's not like just finding the area of a triangle or of a rectangle where both sides are lengths and they're in meters. Here we have different units. That's kind of cool. So when we multiply them together, because we have 4 seconds and 6 newtons, 4 seconds times 6 newtons is going to be 24 newton seconds. That's the impulse. The impulse equals the area, so impulse is 24 newton seconds. The change in momentum from 0 to 4 is pretty straightforward. Why? Because the change in momentum is equal to the impulse delivered by the force. So the impulse is 24 newton seconds, so is the change in momentum. Now we want to find the velocity of the cart at 4 seconds, right over there. We'll use the change in momentum equation. And what's our initial momentum? Well, we look up here where we have our givens. The initial velocity of the cart, it was at rest, so we translated at rest into 0 velocity. So our initial momentum will be 0, okay? So here's our change. Here's our initial momentum. Cancel that right out. So the change in momentum is the final momentum. Switch the equation around. So we have PF is delta P. And what is momentum? Well, it's mvf, right? We're interested in our final velocity is delta P. Divide both sides by m. And then finally put the numbers in, and we get a final velocity of 9.6 meters per second. Now we're going from t equals 4 to 6 seconds. We want to find the impulse delivered. So here's 4, here's 6. So we mark that out as our base. Then we take the area under the force curve. So this time, instead of a rectangle, we have a triangle. So once again, we take the area because the area of this will be our impulse. So for a triangle, it's 1/2 base times height. We put our units in here. The base is 2 seconds. The height is 6 newtons. And then we multiply through, we get 6 newton seconds. And yeah, I kind of switch the newton second around. That's okay. Impulse equals area, so the impulse delivered is 6 newtons per newton seconds. What's the change in momentum of the cart over this period here, 4 to 6? Again, no calculation needed. Why? Because the change in momentum is due to the impulse. So we're repeating this just so it helps you remember it. So our change in momentum is 6 newton seconds. And finally, from t equals 0 to t equals 6 seconds, this whole piece here, what is the impulse delivered by the applied force to the cart? Well, one way of doing this is adding the previously calculated impulse from the 0 to 4 seconds, our blue rectangle, to the impulse from the 4 to 6 seconds, the red outlined triangle, to find the impulse from 0 to 6 seconds. So we add 24 plus 6 Newton seconds and we get 30 Newton seconds. But what if you didn't calculate the individual impulses due to the rectangle and the triangle? Well, hopefully, or maybe you didn't, I certainly didn't do this first time. This is a trapezoid. Okay, 1, 2, 3, 4 slides. And the area of a trapezoid is 1/2 times the base 1 plus base 2, where base 1 here is the longer piece. You know what, let me just erase that because that's not very clearly seen. And it's cool, trapezoid formula is cool. So here's our base, that's base 1, that's 6 seconds long. And here's base 2, that are horizontal parts of this guy here. So that's 4 seconds. And then the height is going to be 6. The height of the trapezoid is this thing here. So we have the two bases added together, times it by the height, and once again we get 30 Newton seconds. That's good, or else geometry would be wrong. So the impulse is the area, so the impulse is 30 Newton seconds. And once more, what's the change in momentum of the cart? Well, it's equal to the impulse delivered by the force. So hopefully after these problems you'll never forget this again. So that will be 30 Newton seconds. And finally, find the velocity of the cart at t equals 6 seconds. We will use the change in momentum equation again. And since we're starting at 0 seconds, there is no initial momentum. So the change in momentum is the final momentum. Final momentum now is mvf. That equals a change in momentum. Divide both sides by m. Plug in the change in momentum for this whole area here, which was 30 Newton seconds. Divide it by the mass and get a final velocity of 12 meters per second.